Thank you, Rob. We appreciate the opportunity to be here. As Rob said, I work for the National Institute of Standards and Technology, which is actually the nation's measurement science laboratory. We are probably the only laboratory that's actually sort of written into the Constitution, because we're the keeper of the nation's weights and measures, and that's actually written into Article 1. So it's a nice place to be. In addition to the physical sciences work that we do in our laboratories in Gaithersburg, Maryland, just outside of the District of Columbia, or you might want to call it dysfunctional capital at the moment, we have a number of other programs, including the Manufacturing Extension Partnership, for which I work, and we are a co-funder of CMTC and MANEX. So if you have manufacturing issues, you can talk to Jim Watson, John Anderson, Gene Russell, or Bill Brown. They're all here and would be happy to talk with you about what you might need. We also have a separate program office that runs the National Network for National Network for Manufacturing Innovation. The first institute is actually funded in Youngstown, Ohio, and it's a subject of additive manufacturing. So California is not alone in this. The difference I see is that California has pretty much all the assets that are needed to do this right. You've got the OEMs, you've got the service providers, you've got the equipment makers, you've got, the laboratories, you've got the service providers who can all help bring this network together into something that will be a powerful force, both for manufacturing, which is important to the administration, finally, and for economic development to really make this work. Let me introduce my two panelists, because I'm not sure where my third one is. He was actually coming up this morning, and I've not heard from him. Perfect. Excellent timing. John McNeil from AeroVironment manages the mechanical engineering department in their unmanned aerial systems segment, 20-engineer group charged with developing the structures, mechanisms, and toolings used in their unmanned aerial vehicles line. They're using 3D printing at the company to manufacture products in energy and aerospace, and they're a world leader in the design and manufacture of unmanned aircraft systems. Originally, our second speaker was going to be Paul Casconi from Argen. Paul, unfortunately, is sick, and Shane Collins has graciously agreed to step in and do his presentation. Shane is also doing a later presentation in the 2 o'clock panel on service providers. Shane began his career in additive manufacturing in 1999 while working for major machine manufacturers in product and business development. He's working for Oxford Performance Materials. And our newest arrival is John Malinzak, who is with the Manufacturing, Engineering, Planning, and Program Integration Group at Pratt and Whitney Rocketdyne. He has over 23 years experience manufacturing, engineering, and operations management, and has supported rocket engine development and manufacturing programs that include the RS-27, MA-5A, X-33, and several others, and that's going to be a really unique application for additive manufacturing. What we've asked the panel to do is talk about what OEMs like them are doing using additive manufacturing technology and techniques today, as well as provide some information to you on what they're expecting from their suppliers, equipment, materials, and parts manufacturers as they go forward with their business. With that, let me bring John McNeil up, and he will tell you everything there is to know about what AeroVironment is doing.
Thank you, Dave. Slides are all set. Well, as Dave's introduction said, my name is John McNeil. I manage the mechanical engineering group for the UAS business segment for AeroVironment. So, oh, that's right, I have control of these. What I'm going to talk about is, for AeroVironment as a market leader, how did we become a market leader in UAS and what did we do? But I say market leader, I'm talking about the fact that AeroVironment has captured all 4 of the small unmanned aerial vehicle program of records that are out there. This means if you look on CNN or the news or anywhere else and you see someone in uniform throwing a UAV, throwing a drone into the air, that's probably one of our systems. We've manufactured about 12 to 15,000, depending on how you count, of these systems and fielded them to all sorts of users. So how did we do it? Well, there was the key was the rapid design cycle. The vehicle that you see in the graphic here that the soldier is launching, that went from a whiteboard sketch to a flying prototype that won a fly-off competition for an urgent need statement in about just under a few months, about around 3 to 4 months. That's not possible with traditional methods. It's a breakout product area. The user they're not working off handbooks. There's no standard for a UAV. There's no prior art for us to look at and say, what do we need to do to give a soldier the ability to see over the next hill or to see what's coming or to follow him in a convoy. We can't compare it to anything there, and the customer isn't exactly sure what they want. So they're not sure what they want, but they have strong conviction that they know they need a solution. So there's an urgency and a lack of clarity. So our approach was build a lot of things fast, iteratively. The product that you see here, fundamentally, it saves lives. And it's not a lot of opportunities as an engineer that works on defense systems that you can say you save lives. It saves lives in a couple of different ways. It's saving Americans, it's saving Brits, it's also saving Afghanis, it's saving Iraqi lives. So it's saving the soldiers' lives pretty clearly. It has prevented IED attacks. It has increased security. It has increased their confidence so they can step back on their rules of engagement, relax a bit. It saves civilian lives because it has prevented mistargeting. It has prevented the collateral damage or civilian casualties that come from a strike going into the wrong place. The eyes on the target, the eyes in the sky, actually have made it such that there are more people in this world alive today because we've been able to field these products. So the message I want to give to this group off this first slide is appreciation. We could not have gotten these products fielded. We could not have had the business success that we've had and the impact that we've had without the capabilities and competencies represented by this group. So to everyone from AeroVironment, from our users, I want to say thank you. I'd like to get into a little bit more details, or as many details as I can, in a public forum. So the graphic on the right shows just a typical product lineup for AeroVironment in silhouette. We're looking at small unmanned aerial vehicles, and when I say small, I mean 2 to 20 pounds. These are fit in your backpack, soldier-carried, hand-launched systems. There are uses of additive manufacturing. It's kind of the typical uses you'd expect of an aerospace manufacturer. We're making flight prototypes of parts that we later intend to make out of injection molded. We're making enclosures for electronics. We're making airframe components, cabling, brackets, the typical type of parts that you would see. We take it a little step further, though, in that we've actually fielded the additive manufactured parts. We've sent them into theater. We've used them in the field, and they've lasted years. It isn't the stepping stone there to injection molding. That is the actual product. So I want to talk about a game changer here, though. We don't field all of the parts in additive manufacturing. We still have to transition to injection molding. We still have to transition to different methods, more traditional methods for making the parts, and we face a couple limitations. For one, a UAV or a drone or whatever you want to call it is essentially a flying iPhone. You take a processor, memory, a radio link, and you put wings on it, and you have the functions of a UAV. Well, ours are more like flying tough books. you take all of those functions and now make them waterproof, environmental proof, and capable of being dragged through the mud, carried by a soldier, carried through the field, and abused in every way imaginable and many ways unimaginable. That's what our products end up going through. The problem that we find within the additive manufacturing sometimes is we don't get that environmental durability. The parts leak. They leak around the O-rings, they leak past gaskets, they sometimes even permeate, leaking through the walls of the part. We got to get that under control to be able to send more parts into theater and use additive manufacturing as the final process. It's got to be predictable. We have to know what it's going to be, not just this year, but 5 years down the road. We may send a UAV out of the plant and not see it again in our logistics activity for several years. The other problem that we run into is the ability to reliably construct thin walls. When you're talking about a UAV that weighs less than a few pounds, every thousandth of an inch matters. We operate close to or at minimum gauge for a lot of the processes out there, either SLA, SLS, or polyjet. We are very close to the smallest size possible. Every bit we can shave off a wall thickness gives us a weight benefit. The problem here is that at a thin wall part, at a 50 thousandths wall, if you have a plus minus 10 thousandths variation in that wall thickness, you're talking about an 80% variation in the critical load capability of that part. That precludes that part from being used as actual load-bearing structure. You know, we've managed to field it, we've managed to do it, but we have to go through a bit of wrangling on tolerances, a bit of wrangling on the process, and it's a challenge. When you go to injection molding, you know you're going to get fairly consistent thicknesses, fairly consistent properties, and if we could get there, the materials are there. The printed material strength is on par with injection molding. So why is it still viewed? Okay, so I'll finish up on this slide actually, because I want to say this one. Printed material strength is on par with injection molding. So it's still viewed as a stepping stone process to injection molding. And the reason is, like I said, the limitations of the part. But actually, let's do one more topic I have. What I want to say here is just what makes, this is the insight into a decision-making process that an OEM goes through on whether we build something in-house or whether we go out to a vendor network. We operate two of these, one Eden machine, one Connex machine, and we have our old SST. These machines are great for our rapid capability. It's hard for the outside vendors to come in and break into the rapid service. The proximity is kind of what drives that. But what we can't do with it is we can't get all the materials we need. Polyjet doesn't do flight, fieldable parts. And if we do start doing production work on our machines, we start tying them up and prohibit the R&D activity from getting in there and getting their fast design cycles. So to close, I just want to point out that little Dimension SST. After 7 years working on 12 different systems and running on its third print head, that can't find a reason to get rid of it. It's still used. Thank you.
Thank you, John. John, could I ask you to come up next and talk about what's going on at Rocketdyne? How do I close that? He has no slides because you remember that phrase John used a minute ago about what I can say in public? Is another guy who can only say so much in public, so there are no slides to go with it, so listen carefully.
And not only can I not say very much in public, I did not have enough time to get the charts approved to release in public, so for this format. So I'm sorry I don't have any slides to present today, but I'll go through some notes that I have. So Pratt Whitney Rocketdyne, or Rocketdyne as we call it, has been in business for 53 years. Our main business is liquid rocket propulsion. And to kind of put it in perspective, we have launched almost every astronaut, U.S. astronaut into space on Rocketdyne's engines. Last year, in 2012, we had 12 successful launches. We had 14 the year before, so we are still launching actively with mostly the RS-68, or our Delta IV engine. RD-180, our Atlas V engine. We have upper stage engines, which is the RL-10, and then there's a few Delta IIs left, which are the RS-27 engines. We have facilities in California. We're headquartered in Canoga Park or Chatsworth now. We're in the process of moving to Chatsworth. We have facilities at the Marshall Space Flight Center, Kennedy Space Center, West Palm Beach, Florida, and let's see, where did I miss? And that's Stennis Space Center is where we do all of our final assembly and test at on the test stands down there. So our manufacturing shop in Southern California is where we have the additive manufacturing machine located and up and running. Our main focus is metal. We're working with the nickel-based superalloys, namely right now, but that was just installed in that factory in May of last year. It was delivered in December of 2011. We had to get a room built to meet all the Southern California building codes. And then we started running it at the end of May. So just in a few short months, we've gone from making material samples to actually making parts. And I'll touch on a little bit of that as we're going through. So the question that we asked ourselves is, why additive manufacturing? And this is going to answer a question that came up earlier about the machining versus just having the parts produced. So why additive manufacturing? It really opens up the design space to design for functionality as opposed to designing for manufacturability. Typical designing or typical manufacturing is the subtractive manufacturing is you have to build it in separate pieces, weld or braze or join the pieces together somehow, then do some final machining on it. But what that does is that it opens up the space to have the designers design it for the way they want it to function as opposed to the way we need to produce it. Will it eliminate the need for manufacturing in the future? Personally, I do not think so. I think there's always going to need to be a need to final machine whatever product we make. We're going to have to continue doing the heat processing. We're going to have to continue doing plating, welding, joining, all those other processes, because right now the technology is not mature enough to hold the tight tolerances that we in our business dictate that it needs to hold. So we took a look at a couple other options before we bought this machine. We have a number of EV welders in-house, and one of them is capable of doing the wire feed additive manufacturing. We started doing some testing on that late last year. Found out that the powder bed machine that we have is far more capable and producible of parts. And so we're really going forward with continuing on with the powder bed additive manufacturing process within Rocketdyne. One thing I do want to note on the additive manufacturing is that it is all internally funded with Rocketdyne dollars. We're not working anything on any of our government contracts. We're developing the parameters. We're developing material properties. We're working with our materials group, our engineering group, our design group to completely produce that and develop that in-house. And then just last week or 2 weeks ago, J2X had an engine test that there was a part that was produced using the additive manufacturing process, and it was a 625 part that they did get onto one of their engine tests for a 560 engine test. They've taken that part off. They're going to evaluate it. But there's a number of pieces that we're going to be swapping in and out of that test program to see how the materials react in the environment that we're going to be putting them in. Okay, so with the design of experiments that we're doing, we're looking at the parameters across the spectrum of the machine that we have that is capable of producing. And what we're really doing is we're producing a new material form. But what we compare against for when we're doing the testing is we compare against the heritage wrought or cast AMS materials for the super-base nickel alloys. And right now we're somewhere between the casting properties and the wrought properties of those alloys. So again, in the short 9 months that we've been working with this machine, we feel that we've come a long way in developing the process of additive manufacturing within Rocketdyne. Taking a look at the tolerances, we do have a number of pieces that we do some white light or inspection on after the fact just to see how the material is reacting. Typical engineering requirements that we're getting are within plus or minus 10 thousandths. The parts that we have measured, and it's about a 5-inch diameter piece and a couple inches thick, we're getting it to be within about 4,000. So it's very repeatable and very predictable. So we're happy, we're pleased with that. And we're going to continue taking data right out of the machine, pre and post heat processing, cutting it off of the build plate and taking a look at it through the entire life cycle. Okay, so I guess in short, in closing, you know, we have been working with the other machine owners within the United States. Lawrence Livermore happens to be one of them. We have a monthly telecon with them. National Marshall's another one that has a similar type machine with us. And the purpose of those talks is really just to get together, share some of the lessons that we've learned, some of the issues that we're having with the machines, maybe help them along to get everybody up to the same level that we are, or that they are in some cases, just to make sure that we're growing and maturing evenly across the industry. And that's all I have.
Thank you, John. Part of what you see and what John talked about is the beginnings of that certification qualification process that's going to be required for aerospace kinds of applications. They're not the kind of things that just happen. We'd like to say, yeah, they're the right kind of super alloy, but until you go in and actually compare it against what's available today and qualified for flight, you don't really know. With that, I'm going to turn this over to Shane Collins, who's going to do a real good imitation of Paul Cascone and talk about dental materials and alloys.
So part of the invitation began this morning when I put my tie on. Paul would have appreciated that. So that's the way it had it. A couple of comments earlier, because I'm going to have a lot of time doing someone else's presentation. I'm not sure how this is going to last, how long it will last. But to the comment about subtractive manufacturing and where should we be putting our emphasis on education, my perspective is that currently what we need is more emphasis on merging the technologies of additive and subtracting because of some of the negative impacts of additive manufacturing, be it tolerance or whatever it is, to take this really expensive preform that we made and then turn it into a usable product. So that needs a lot of work. And then I'm going to give a shameless plug out for the ASTM F42 committee on additive manufacturing because we are writing some standards for additive manufacturing. I'm the chairman of the F4205 Materials Subcommittee, Materials and Process. If there's anyone who feels compelled to write standards, it's great activity. Our next meeting is in Nottingham, England in July, so we would welcome that work. So let's talk about dental. It was in the year 2000, I was in a room with probably a little more people than this, and I was giving a presentation about additive manufacturing, which at the time, additive manufacturing didn't even exist, the term, it was 3D printing. And I told the crowd that we were going to replace what they knew today as the process of making copings and bridges with 3D printing. And I got a lot of blank stares. But from that original discussion to where we are today, that's really what has happened. So we've taken a very labor-intensive artesian process, automated it with additive manufacturing to create really a new industry. Argen is a company based in San Diego. Their primary business is supplying the precious and semi-precious alloys to the dental industry. That would be your gold, palladium, platinum, and also the base alloys of cobalt chrome. They have distributors around the world, and visiting their plant one time is the only opportunity I had to actually hold a full gold bar in my hand. That was kind of interesting. You can imagine the security going in and out of their building. You think it's bad here? They actually weigh the metallic ions in your body before the employees are allowed to leave. So that's a true story. Their goal is in making people's teeth look better. And so they do that by supplying the alloys that are used in the process to create a porcelain fused to metal restoration. So you have a gold or a precious metal that is traditionally, it's a casting process. As you can see here, this is a wax pattern that will be sacrificed in the casting process. And you have them sprued up, and here you have two copings that would eventually have the porcelain fused to it and then colorized. And when you go to the dentist to get a crown, this is an option. The problem is that creating this, this coping, or in some cases it's a multi-unit bridge, is that the labor force to do this is dwindling. No, it's difficult to get people to want to sit at a desk for 12 hours a day in some cases and do this very tedious work. So the labor force is dwindling, as well as there's a need to make these more efficiently and less expensive. So enter into the process of ASTM terminology. This is called powder bed fusion. And subset of powder bed fusion is metal laser sintering. So what you see on the screen is a layer that is being laser melted, where the heat source is hitting the surface and melting a cross section. Each one of these would be a coping or bridge, and the productivity is such that in one 24-hour cycle, you can do 200 or 300 of these restorations, where an individual sitting there doing it the old-fashioned way could maybe do 15 or 20. So it's a great productivity increaser. What has been Argen's contribution to this process is that the alloys that they use and people want to use in dental are not readily supplied. So they have created their own laser sintering alloys in-house. They atomize the material to make the powder, and they've created their own specially made laser sintering alloy. Qualifies as a precious metal, but yet is less expensive, and it takes advantage of the additive manufacturing process, this being in an inert environment as it's being processed. So just to take you through the process of how it's done, you have a scanning process and then a design where a pattern is scanned, reverse engineered. You create the model in CAD, create the STL file that's used. It goes directly into the machine. Here you see a coping that's right out of the machine with the supports still attached. This is how it was connected to the build plate. And some close-ups of what that process looks like so that you can see that this is a fully dense structure. It's not centered. And if you look at it under a microscope, you'll see that there's no porosity. Now, technically it's a challenge because you're talking about a wall thickness here, 0.3 of a millimeter, so it's a very thin wall. And the precision has to be such that the cement they use to glue it into your mouth doesn't allow any inclusions, bubbles, or it's a tight bond. So it has to be highly accurate, very thin wall, and that's a challenge with the equipment that's available today to do this process. So in summary, the challenges as an OEM and what an OEM faces from trying to do 3D printing of powder bed fusion. First of all, and this is a general statement to all the machine manufacturers, some of which I know are in the room, there are no two machines that are alike. That's just the reality. They're more or less hand-built machines. The parameters you use in one won't work in the same machine, even though it's serial number sequentially one different. That's just the reality. So there are not the feedback control mechanisms inside the machine that control the process. They're open loop. So once you start the machine, the laser power, the beam size, how close together you make your stripes, the length of the stripe, that all plays an important role into making sure you don't have any porosity. But how do you know that that powder layer was distributed without any anomalies? We don't. That's the reality. So the research is going on now, and some people are looking at how do you put sensors in to monitor the melt pool? How do you put sensors in to make sure the powder level is correct? And with the future of that, the machines will be more robust, like you would expect from a machining center. Powder handling and part removal. So this goes back to traceability, and is a difference between making a rocket engine that has to have safety critical components and process specification versus making some of the consumer items that we may have seen earlier. The difference is that you have to have traceability of the feedstock, and you start using words like that instead of material, all the way back to when it was originally mined out of the ground and then melted and gasolinized into a powder. We have the ability, luckily, with these machines to reuse the powder over and over again. Okay, so how did you get the powder out? What happened to the powder when it was out? How did it come back in, and how do we know that it didn't change in contamination, particle size distribution, chemical contamination, all those kind of things? So we have some unique requirements in additive manufacturing for controlling the process. And the machine manufacturers are addressing it, but I think there's still quite a ways to go. That's it. Thank you.
We're going to use this microphone to do questions. We've got about 10 minutes, so anybody with a burning question on your mind? Up in the back.
I was just wondering, for building up layer by layer, is there any concern about having micro cracks between layers, or is there any stress concentration issues? Concerned about?
To me? Or
I guess one of the Rocketdyne
Repeat the question. Probably applies to all three of you at some level, so just repeat the.
Get you here.
So the question, the way I heard it was, are we looking at any micro cracking between layers as we're building it up layer by layer?
Right. So, are there any concern that could be stress concentration, because each layer could have some differences when you build it up, and could there be inherent cracks, and whether you need to deal with crack growth issues, things of that nature?
But that is one of the things that we're looking at as we're going through the development, and we're going to have to at least, as we're getting the specs, like was said earlier, as we're developing the parameters and we're taking a look at it, and we go through the design of experiments and we narrow it down, we're looking at not only, and once we get to the melt pool understanding, we'll be able to better identify if there are issues from layer to layer. But we are taking a look at, as we're doing the or the material properties and the sectioning of the samples that we're doing.
So you're still doing investigations?
We're still doing investigations.
And the alloys that you're developing, is it proprietary?
No, it's 625 is the one that we're working with most right now.
Okay. All right, thank you.
Along similar lines for the aerospace and the medical applications, are you, in parallel with developing the specifications, looking at non-destructive inspection methods? Sounding like you're going to be looking at things that typically be applied to castings or other end products that are very process-oriented in their final capabilities.
Well, I'll talk from my side. So the question is are we looking at the NDT standards as well as the material properties? In our case, yes, we are. We're taking a look at how we're going to inspect it once we get these built, not only dimensionally, but X-ray, penetrant inspection, all the other post-processing that we're going to have to do. So we are looking at the whole gamut of NDT inspections that we would have to do in order to qualify and then continue to use the materials.
Is that work being published, like in ASTM kind of specifications, or is that all going to be Rocketdyne proprietary?
Well, right now, everything is being developed internally, and so right now we're considering it to be Rocketdyne proprietary on what we're doing.
I was just going to add that NIST is actually having a conference in Baltimore on non-destructive testing of additive manufacturing. So it's a good question, and that's, I believe that's in July. So if you'd like to come up, I can give you the coordinates for that. And the inspection criteria for additive, from what we've seen in powder bed fusion, this would be with an electron beam or a laser beam as a heat source. The types of defects are different than you get with a casting. The porosity is usually much finer. You don't see it on an X-ray. The surface finish as built doesn't respond well to the liquid penetrant, so you need to have other criteria for your inspection. And it is something that people are looking at. So micro CT is probably a good inspection method. It's very slow, and it's expensive, right? But those are the kind of things that may be required.
Do you see that qualification and inspection processes pacing even the materials development in terms of actually being able to field a part on a rocket engine or in the medical industry?
So the question is, the non-destructive testing aspect of additive, is that going to pace the development of the alloys? And so far, what we're trying to do is get the existing alloys to work in the process correctly. So you were talking about your high nickel super alloys, Inconel 625, 718, Hastelloy, those kinds of alloys. And then you have the titanium, Ti 64, Ti 64 Eli. By the way, there is an ASTM standard, it's F2924, give myself a shameless plug here, for Ti 64 with powder bed fusion. So if you build to that ASTM standard, you have a pretty good chance of making a good part.
Thank you. I'm Wayne King from Lawrence Livermore. I'd like to address that question of whether certification procedures would be published. We're involved in developing accelerated certification methodology here for a variety of metal parts, and it's our intent that these procedures and codes and things like that we're using for doing that will appear in the open literature, and that the codes will be shared with other companies or other laboratories that need to be able to model the additive manufacturing process. So I think the answer to your question is we're going to be doing that, and that's a major focus of what we're doing in the near future.
One more, and then we're going to turn it over to the next panel.
My question is about heat treating. Do you heat treat as normal, surface finishing, all that? Do you treat these materials the same way you would with a cast or machining process? How does that work?
So the question is heat treat processing and surface finish processing. You know, there are some companies out there that have some proprietary micro finishing that they do. We have not gotten into that. We're just purely focusing on the material properties right now. We are looking at ways to post-process for surface finish. I'm in parallel. But as far as I have seen and what we've worked with, it has just been the normal heat processing that we've been doing after the fact.
I just wanted to add one thing to that. What we found generally is that additive manufactured metallic parts don't respond quite the same as raw material does, right? So if you're expecting a 17.4 stainless steel part to heat treat with H900 the same way you would expect a rod part, you probably will be surprised. So there's a lot of work to be done in heat treating and the thermal processing, but generally speaking, you can hip the parts, and you can be pretty well assured after hip that you won't have any porosity. So it's a good part. So at least that is fairly standard.
So we have ways to go.
Yes.
Part of what you've heard, though, is there are lots of opportunities for new research in non-destructive testing methods that are going to have to go in parallel with this, as well as a lot of materials and equipment development that will probably keep us gainfully employed for the next 25, 30 years, give or take a couple. With that, let's thank our panelists.